I'm Anil Kumar. Welcome to my series on trigonometry. We'll begin with basics in part 1. To get started, you should be very clear about how to solve equations involving ratios, that is to say, something of this form, a over b equals to c over d. So to solve this equation, we have to cross multiply, right? So a times d equals to c times b. That is one concept. The other concept which you should know is Pythagorean Theorem, which is if I have a right triangle, shown here for example, in this right triangle, if the sides are A, B and C with right angle at the vertex C, right? So when I write A, B, C, the vertex opposite small a will be A. So here the sides are related with the formula a square plus b square equals to c square. So that actually forms the basics for us to start with trigonometry. Then we'll take up right triangle trigonometry, defining what tangent ratio is, and then the terms sine and cosine, and also find how to solve such a triangle, that is, how to find out the angles. We'll use Greek alphabets, alpha, beta, gamma, theta for the angles. Now in part 2, I'll take up applications to solve right triangles. All the concepts which you have learned in part 1 will be applied. Okay, so let's begin. Getting started with ratios. So I've taken up very simple equations. X over 4 equals to 7 over 20, 12 over x equals to 9, 2 over 5 equals to 3 over x. Now x has different positions. You should know how to solve it. Cross multiply is the strategy, right? So the strategy is to cross multiply. So here is easy solution. When you cross multiply, you could write this as 20x equals to 7 times 4, and then again you could write x equals to 7 times 4 over 20, correct? Now my suggestion is that when you work with such an equation, rather than doing all this, right, so avoid all this. What you should do basically is that straight away you know where x is, correct? So in this particular situation, since we know that x is right there, we only do not want this 4 here. So what we will do here is that we'll write x equals to 7 over 20 times 4. Very simple. Now that is how we are going to do, and we'll avoid one step. So I hope you understand the strategy here. So this will give you, when you divide this by 5, you get your answer 7 over 5. Is that clear? So that is how we are going to solve our equations. Now let's do these two using this kind of strategy. So we do not want x in the denominator, we want it somewhere there. So I'll just swap the positions. So we get 12 over 9 equals to x. And now we can simplify this, dividing both by 3, getting 4 over 3 as the value of x. So I hope that is clear. In this example, x comes to the left side. On the right side, we already have 3. And now we'll bring these two terms, cross multiply. So we get 5 over 2. So that gives you x as 15 over 2. Is that clear? So that is the way we are going to solve all our equations. We'll avoid this kind of strategy. This involves an extra step. So I hope that is absolutely clear. So cross multiply, isolate x and solve. Now we have taken up two quick examples on Pythagorean theorem. We want longer side, right? So in this case, these angles are 90 degrees for you. Since we want the longer side, it should be sum of squares, right? So we know c square is 3 square plus 4 square, and c should be equal to square root of this, which is 9 plus 16, and that gives you square root of 25 or just 5, correct? In this case, we want to find x, and x is not the hypotenuse. It is smaller. Since it is smaller, you don't really have to think much. You can write x is square root of 13 square minus 12 square. Does it make sense? Since it is a smaller side, right? So don't really get into a square, b square, c square things. This is much better and faster. So you know this is 169 minus 144. So I've taken very simple examples, ideas to illustrate the process rather than get involved in calculations. So we get x equals to 5 in this particular case. So with that, we have done the review, and now let's begin with trigonometry. Right triangle trigonometry. To begin with, let's again take the right triangle. We just solved a right triangle using Pythagorean theorem, right? So here is a right triangle, right? So we'll assume this to be 90 degrees. Now, what you really saw here is that you could find sides for this particular triangle. If I give you the length as, let us say, A and B, right? Let us say A and B. In that case, I know what C is, right? I can find what C is. We know C square equals to A square plus B square, and that gives you that C is equals to square root of A square plus B square. Now the question is, how do we find the angles? We know that is 90 degrees, but how do we find this angle theta? Now that's a big question. How to find angle theta? All right, so that results into what we'll talk about, the tangent ratios concept. So that is the question which is being addressed now. What you also notice here is that if I have similar triangles, that is to say, if I draw lines parallel to this, for example, like this one, or maybe much smaller. So for all these lines drawn, we have different triangles, correct? So this is a smaller triangle, bigger triangle, so we have similar triangles. Let's write triangles like this. So in all these similar triangles, the angle theta is same. Also, what do you notice? Also, you notice that the ratio A over B is constant. Let's say these sides are A dash over, let's say, B dash. In that case, the ratio A over B is equal to the ratio of A dash over B dash. It is a constant. It never changes. You may even extend, even then the result will be that the ratios are same. Perfect. Now, if you relate A over B with kind of slope of a tangent line, that is rise over run, so rise over run is A over B. So that gives you some clue that since the angle is constant, right, which is related to the slope, normally we refer to it as m, we have come up with a new mathematics area which is called trigonometry. So here, this particular slope is now given a term as tan theta, and we say tan theta is equal to A over B. So that is a new term which gives rise to trigonometry. So I hope this concept is clear. Now if you look into this angle, we could always say from the angle theta, A is opposite side. And B is adjacent side. So from now onwards, we'll treat tangent ratio tan theta as a ratio of opposite side to the adjacent side in a right triangle. Perfect. So that is the term, and that is going to help us find what theta is. So we have related the angle in a triangle with its sides. So that's a huge concept. I hope you understand and appreciate it. Now let's take a few examples and get into its details. Now we will extend the basic concept of tangent ratio for an angle to slope of the line. So let us consider a few lines now. So here is our coordinate plane, and let us say we have a line which is somewhere here like this. Okay. In that case, we can always find the slope of the line by calculating rise over run, right? So for this line, if we consider a point on the line, then the value of rise over run gives us the slope, right? So for any line, what we have here is that the slope, which we consider as m, equals to rise over run. Now if I have a line which is y equals to x, let us say, in that case any point here will be having same x and y value. So let me consider this point to be 5, 5. So that really means that rise is 5 and the run is also 5. And the slope therefore is 5 over 5, which is 1. We know that this line divides the plane, which is xy plane for us, diagonally, and we also know that the angle which is made here is 45 degrees, right? It bisects, so it is exactly half of 90 degrees. Correct? So this line, if it is y equals to x, it will diagonally divide the plane, and the angle which it makes is 45 degrees. So from this knowledge, what we can say is that tan of this angle, let's call this angle as theta, is equal to 1, and here theta is equals to 45 degrees. Does it make sense to you? Right? So we can directly relate slope with the tangent ratio, and then also relate angle with the tangent ratio. Correct? So we can say if tan theta equals to 1, then theta equals to 45 degrees. Does it make sense? So we are trying to create a relation between the two. Now let's consider a few other lines. For example, if I increase the slope of the line and draw the next line going through the origin, kind of like this. Let's say this line is y equals to 2x. Now for this particular line, we know tan of, let me call this angle as phi. We are using Greek symbols here. Let's say this angle is phi, is equal to rise over run, which is same as the slope m. So it is going to be 2. Well, it really makes sense, since any point on this line, the xy coordinates will be what? If x is, let us say 4, then the y coordinate is twice 4, it will be 8. So in that case, we know tan phi will be equal to rise of 8, run of 4, which gives you the value 2 itself. Perfect. Now, as we increase the slope of the line, if we increase it further, what happens? So you see that as we increase the slope, tangent ratio, let's call it as tan of theta, increases. Correct? What happens when it is 90 degrees? So what I'm saying is, what is tan of 90 degrees equal to? Now in this situation, when I increase it to the limit of 90 degrees, in that case, any point here will be treated as, let us say this point here is 9, 0 for x, y value of 9. The y-intercept is 9. So for that point, rise is 9 and run is 0. So we have something like 9 over 0, which is undefined. So if the angle is increased to 90 degrees, we get a value which is undefined. On the other hand, if we consider decreasing the slope, that is bringing this down to 0, and if you want to figure out what is tan 0 degrees equals to, then any point here could be considered as the x-intercept where the x value could be, let's take some value, right? Let's say 6 and y value is 0 for sure, right? So it is equals to 0 over 6. Now in this case it is 0. So what we say here is that the slope is 0. And tan ratio, let me say tangent ratio, is 0. Correct? So what we have noticed here is that in a right triangle, tan theta is a value which is greater than 0 degrees, right? So here there is no limit, right? It goes to undefined value, so I can just forget about this limit. It is from 0 to anything if we are only considering this angle, right? Now, let us extend this to lines with negative slope. So we could have a line which could have a slope which is negative. For example, this line. Now let's say this line is y equals to minus, now let's say 3x. Now since the slope is negative, tangent ratio is also negative. So if slope is negative, tan theta will be negative. So from here, what do you conclude? From here we conclude that tangent ratio can have any value. Perfect. So from here we conclude that tan ratio can have any value, right? So what do we conclude here? We conclude that let's write tan theta can have any value. That means a real number we are talking about, right? So it could be from minus infinity to plus infinity. So we could write this as from minus infinity to plus infinity, any value for tan theta. So that is how we could actually say that tan ratio could have any value. Its value relates to the slope of the line on a coordinate system. And with that simple comparison, we also see when will it be 0, when will it be infinitely large. So if the line is along the x-axis, it is going to be 0, but if the line is along the y-axis, it is going to be infinitely large. If you have a slanting line going downwards, then the value of tan ratio will be negative. So I hope that makes sense. Now let me introduce you to other trigonometric ratios. So we'll again sketch a triangle, right triangle. So we are working with right triangle at present. So here is a right triangle. Let's say the triangle is ABC. Now in any right triangle, we'll label sides as vertex A, side opposite to A will be lowercase a, side opposite to B will be lowercase b, side opposite to C will be lowercase c. So from here, we already know that tan of angle A is equal to opposite over adjacent side, right? So that is, it is equals to A over B, right? Now, the ratio for other sides is also constant. We could have ratio of opposite to hypotenuse, right? So we could have some ratio which could relate opposite side with hypotenuse. This ratio is called sine of angle A, and cosine of angle A will be the ratio of adjacent side to hypotenuse. So these are the other three ratios which we are going to work with. So here we have hypotenuse. This side, which is adjacent to the angle we are talking about and 90 degrees, is called the adjacent side. And that side, as you can see, we are considering angle A for the time being, so it is opposite to A. Does make sense? So with reference to angle A, we have all these new trigonometric ratios. To remember, what we really do is use an acronym which says SOHCAHTOA. Sine S is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tan is opposite over adjacent, correct? So that is the acronym which we use to find trigonometric ratios. Now all these ratios relate angle with the sides of a right triangle. Perfect? So in our case, sine of A is going to be what? A over C, right? So it is A over C, and cosine of A will be B over C, since B is the adjacent side. Does it make sense to you? Correct? So SOHCAHTOA is an easy way to remember trigonometric ratios. They are always ratios of sides of a triangle. Tan relates opposite with adjacent, sine relates opposite with hypotenuse, and cosine adjacent with hypotenuse. So if hypotenuse is involved, we are working with sine or cosine. If not, then we are working with tan. So examples for tan will be, let's say examples could be height, distance questions. Correct. So when we talk about height and distance, we are normally working with the two smaller sides of a right triangle. Perfect. Now here, these examples could be wide variety, where we are interested in the hypotenuse, could be length of a string, for example, in case of a kite, or ladder, for example, etc. Right? So those are the practical situations where we are soon going to apply our learning. Now here is a question for you. The question for you is, how are sine, cosine, and tangent related? Think about it, right? So the solution is right here, but just think about it. So what we could do here is that we know that tan is A over B. Let me show you the relation. Tan A is equal to A over B, right? Now relate tan with sine and cosine. What I could do is that I could divide both numerator and denominator by hypotenuse. So we get A over H, which is C in our case, which is A over C I should write, and B over C, the hypotenuse. Do you see that? Hypotenuse is C, so A over C. So what we get here is the opposite side A divided by the hypotenuse is sine of A. So we get this as sine of A, and the denominator is B over C, which is adjacent side over hypotenuse, which is cosine of A. So here is a very, very important relation to remember, and it is that tan of an angle is always equal to sine of an angle divided by cosine of an angle. Of course, cos of A should not be equal to 0, since you cannot divide by 0. Does it make sense to you, right? So this particular part of the video, you have learned the three primary trigonometric ratios. We call them primary trigonometric ratios. And their relation with one another. Now, let's take up some examples to calculate these ratios in a right triangle. Now, let me sketch few triangles here, and we'll try to find the value of our trigonometric ratios, right? So I'm sketching one triangle like this, the other one kind of like this. So let's write down some dimensions for these triangles. We know we could use 4, 3, and 5. That is very standard. We know in a right triangle, a square plus b square is c square, and we do get that kind of a value. Now here, I will take different kind of values. Let us say this side is 2 and this side is 1, and we have to find the trigonometric ratios, correct? So I'm only giving you two sides of this triangle. You have to find the third side and then the trigonometric ratios. Now let's say here we have A, this is B, and this vertex is C where we have 90 degrees. Let's call this as P, Q, and R. So the idea is you need to find what is sine of A equals to, what is cos of A equals to, and what is tan of A equals to, right? In this case, let's find what is sine of Q equals to, what is cos of Q equals to, and what is tan of Q equals to. Now, if you look from angle A, which is the opposite side? Side opposite to A is this. So this is opposite, and this one is adjacent. Here clearly we have hypotenuse. So it's very easy to write. Sine of A is 3 over 5. Cos of A is 4 over 5, and tan of A is 3 over 4. Perfect. Now in the other triangle, we are trying to see from Q. So if you see from Q, side opposite is this length with 1 units. And of course, this is hypotenuse, and that becomes the adjacent side. So adjacent side is a side which involves the angle and 90 degrees. You understand now. Perfect. Now in this particular case, we don't know the third side. So let's find. So you could use Pythagorean Theorem to find the third side, which is QR, and that has to be square root of difference of squares, since it is smaller. 2 square minus 1 square. Perfect. Which is 4 minus 1 square root, which is square root of 3. So here we get square root of 3 as the side length. Now we can write down what is sine Q. So sine Q is opposite side 1 over 2. So it is half. As far as cos Q is concerned, it is adjacent side of square root 3 divided by the hypotenuse of 2, and tan Q is square root 3 divided by 1, which is square root 3. Perfect. So that is how we can actually find all the sides and their ratios. Perfect. So at times you may use Pythagorean theorem to find the missing sides and then the ratios. Now I like you to verify if tan A is equal to sine A divided by cos A. Okay? One thing, this is what I would like you to verify. Second, I will also like you to find what is sine of P and how it is related with cos of Q. Correct? So that is to say, if you see this triangle from the side P, in that case, you know, sine will be opposite side of square root 3. So this will be square root 3 over 2, which you can see same as cos of Q. Perfect. So that is also a very, very important conclusion. So in any triangle, we call this as complementary relation, right? So we'll talk about this later. So in any triangle ABC, if C is the right angle, in that case, I could conclude that sine of A will be also equal to cos of B, right? So see from B. From B, adjacent side is this, which is 3. And the hypotenuse is same as 5. So do you see that? They are equal. So it's a very important thing to understand right in the very beginning. And it's going to help us when we take up some application questions on trigonometry. Now let's talk about few thinking questions related to the basic concepts about trigonometric ratios. Question number 1 here is, in a right triangle ABC, where angle C equals to 90 degrees, sine A equals to cos B, is the above statement always true, sometimes true, never true, or we have insufficient information? What do you think about it? So let's consider a right triangle and try to answer this question. What do you think is true about it? We have discussed this earlier. C is 90 degrees, and let's say these two angles are A and B. So if the sides are A, B, and C, in that case, what is sine A equals to? Sine A is, looking from this side, opposite side is A, and hypotenuse is C. How about cos B? As far as cos B is concerned, we have to look from the other side, right? Opposite side now is B. However, cos is adjacent over hypotenuse, right? So it is A over C. So what do you notice? Both are A over C, correct? So what we see that they are both equal. So in a right triangle, always these complementary angles, we know cos B is 90 minus A, right? So we can conclude from here that cos of 90 minus A is equal to sine of A. Perfect. Since this is 90 and this is A, then the other angle here will be 90 degrees minus A. Perfect. So it is always true. This is a very important conclusion which we have drawn from this particular question. Now let me take another thinking question. The question here is, the maximum value of sine A is 1, 10, less than cos A, or infinitely large. To answer this question, let us look at our right triangle, right? So whenever we're talking about these trigonometric ratios, it is a good thing to always consider these right triangles. So in this right triangle, we have 90 degrees right there, and we talk about this angle A. Now, what could be the maximum value of sine A? Let's recall, sine A is opposite side over hypotenuse. Now, as you know, hypotenuse is always greater than opposite side. Right? So this is the opposite side and that is the hypotenuse. However, there could be a situation when I increase this angle, right? So if I increase this angle, for example, let's say like this, then forming different triangles, what we notice is that length of opposite side increases, right? So if I increase it to the extent that it is 90 degrees, then you could think about opposite equals to hypotenuse, right? So if angle A equals to 90 degrees, then opposite side is length is equals to hypotenuse. Perfect. So in that case, sine of A will be equal to 1. So that is to say, when angle is 90 degrees, in a right triangle, that could be the case, right? So that is just looks like this, where the base is 0, right? So hypothetical triangle, but still, you could think about it in this situation. Or on xy plane, you could think about a point here whose coordinates could be, let's say, 0 and 5. For this coordinate point, the value of sine will be 1, correct? It's because in this case, opposite side is equal to hypotenuse. Perfect. So therefore, the maximum value of sine could be only 1. It cannot be more than 1. Now less than cosine. For angle of 45 degrees, we know sine of 45 degrees is equal to cos of 45 degrees. Reason being that for this we have an isosceles triangle. So if this angle is 45 degrees, in that case the two smaller sides of a right triangle are equal. So the opposite side is equal to the adjacent side. So in that situation they can be equal. Perfect. But if the angle is more than 45 degrees within the right triangle, then sine is higher. But if the angle is less than 45 degrees, then cosine is higher. Perfect. So this is the learning which we get from this part of the video. Now, I'd like you to practice and find trigonometric ratios for given right triangles. So we have two right triangles here. You may have to pause the video and answer these questions. You can find what is tan A equals to, what is sine A equals to, what is cosine A is equal to. Also figure out what is tan B equals to, what is sine B equals to, and cosine B equals to, right? In this triangle, we'll try to find what is tan D equals to, what is sine D equals to, and cosine D equals to, and also find what is tan F equals to, what is sine F equals to, and cosine F equal to, right? Also see which ones are equal, right? So if you have something, you might get sine D same as cos F, right? They may be equal. So here is something which you can practice. You may find that cos D is equals to sine F. Perfect. Now here it is a very special question. We're trying to find trigonometric ratios for angle of 90 degrees. So think about it and then kind of get it, right? So I'll put this as thinking part. Correct? So this is in general. Normally we find like this. Is that okay? Now that brings us to the end of our part 1, where we learned few things. Let's summarize them. First thing we learned is the tangent is tangent of an angle is equal to ratio of opposite side to adjacent side. We're talking about right triangles. Let's remember that. So let me make one here. It will help to explain things better. So let's say this is our right triangle, ABC. So in that case, tan of A is equal to BC over AC. We learned that other trigonometric ratios, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan, as you can see here, is opposite over adjacent. So for this particular triangle, we could write sine of A as opposite side BC over the hypotenuse AB, and cos of A will be written as AC over AB. You also learn that sine of A will be equals to cosine of B. Perfect. And you also learn that tan A is equal to sine A over cos A. Perfect. And something more than that which we learned is that tan, let me write theta in general, can have any value, right? Since it is like slope of a line, correct? So that means the values could be from minus infinity to plus infinity. You could have horizontal line, vertical line, you could have sloping downwards and going upwards. Perfect. And you also learn that maximum value for sine A or cos A is 1. Right? For sine and cosine, the value cannot be more than 1. That's the maximum value. So I hope with this, we'll close this part and take up inverse of trigonometric ratios in the next part, along with how to find the angles and solve triangle completely. I hope it was helpful. Feel free to write your comments and share your views. If you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.